Section 4.6, graphing other trig functions. So what we're going to do is we're going to graph the next four. If you can do sine, cosine, and tangent, you can graph all of the others because they're reciprocals of each other. We'll talk about that when we get there. The main difference between sine, cosine, and tangent is that tangent has no amplitude because there is no max and min, and it has asymptotes for sure, but so do the other three that we're going to be dealing with. And the period is based off of pi, not 2 pi. But in general, a lot of it's the same. So I'm going to go ahead and pull out the 3 and then set up my little graph. Okay, so I took the 3 out, did a quick distributing in my head to make sure that it was actually right. It does, matches. Take out my little graph now. Now my little graph, I've got asymptotes. Oop, that one didn't come out very dashed. No. And I've got what kind of looks like a little cubic. So I'm going to go through and do the exact same thing that I did previously. I'm just going to use my little graph to help me figure out what my points are going to be. And I am going to have 5 values just like I did with sine and cosine. All right, so the first thing that I see, and I'm going to go in pi over 2 increments just like I've been doing, and I'm going to start at negative pi over 2. So right here, that's my first one. So negative pi over 2. I have an asymptote there, which means this is going to be undefined. Then I go, oh, I'm sorry, I lied. I'm not going to go by pi over 2 increments. I'm going to go by pi over 4 increments. Then I'm going to go to negative pi over 4. I apologize. And that's going to give me a negative 1. Then at 0, I'm going to be at 0. Go another pi over 4. That's going to get me 1. And then I'll go another pi over 4, which is 2 pi over 4, which is pi over 2. So with tangent, I know that the beginning and the end are always going to be at pi over 2's, and it's going to be undefined. Then I go in increments of pi over 4 in between. All right, so let's go ahead and do our transformation now. So it looks like I'm going to take my x's and divide them by 3, and then my y's I'm going to times by 2. So I'm going to pause. And normally I'd be showing more of this work, which I did back in 4.5, but this is just transformation, so just keep repeating the exact same thing we've been doing. So pause and see if we match. Okay, so now I've got my first points for my x and my y. You notice I divided by 3, so now I have the denominators that don't match. I'm going to fix that. And then I took my y's and I times them by 2. Now, one thing to keep in mind, hopefully this goes without saying, but I'm going to say it anyway just in case. Whenever you have a y value that is undefined, so you have an asymptote, if you multiply it, it's still undefined. If you add or subtract, it's still undefined. So it's not going to affect the undefined at all. What was undefined stays undefined the entire time. So please keep that in mind. All right, so now if I take a look at this, it looks like I need some denominators of pi over 12. Let's go ahead and do that. And again, you don't have to do this. I only do this because I think it makes the graphing a little bit easier to do. Plus, then if I have to add or subtract anything, which it looks like I do, then I already have my common denominator, and of course I'll fix that one as well. All right, I check my distance between these. It's all 1 pi over 12 distance. Take my x's. Looks like I'm going to add pi over 3 to them now. Well, I've got denominators of 12. So instead of adding pi over 3, I am going to add 4 pi over 12. Okay, just get that common denominator. So I'm going to go ahead and set up my last table. Okay, so here's my last table. Excuse me. So I know I needed to add pi over 3, but I had denominators of 12, so I went ahead and turned it into 4 pi over 12. Went ahead and added them. I like this because, again, I know I keep repeating myself, but I like to see that my x's are the same distance apart from each other. If they're not, I made a mistake. But the problem is with all the denominators being different, I may not necessarily see that. Okay, notice that my undefined stayed undefined the entire time. Now, I just need to graph this thing. So let's see. I need all positive x's And I need positive y's and negative y's. All right, so got our graph here. All right, so I'm going to start at 2 pi over 12. Well, let's see if this will fit. So there's 2 pi over 12. 3, 4, 5, 6. All right, it fits. It looks like I need to go down to -1, up to 1, and to 3. All right, so at 2 pi over 12, looks like I have an asymptote. Then at 3 pi over 12, I'm at -1. 4 pi over 12, I'm at 1. 5 pi over 12, I'm up at 3. And then 6 pi over 12, I have my asymptote again. Okay, so I have this, my 3 points in the middle. Remember that a tangent curve looks like a cubic, basically. So let's go ahead and give this a nice smooth sketch. All right. So there's that one period of our tangent graph. All right, now that we've had it, we can go ahead and identify everything that's being asked of us. All right, so if I ask you about amplitude, you tell me no, none, there aren't any, or it doesn't exist, it doesn't apply, it doesn't make any sense at all. But if I ask you about the vertical transformation is basically my way of saying, okay, I realize there isn't an amplitude here, but can you tell me what's going on? So for my vertical transformation, take a look at the 2 in front. So it's a 2, so now I go back to my knowledge of transformations from first semester. It means it's going to be stretched vertically by 2, or a vertical stretch. And you don't have to say vertical because it's a vertical transformation. So you can just say stretch by 2. But I'm in a habit of saying vertical or horizontal because of transformations from first semester. So if you are too, just go ahead and keep writing what you've been doing. So vertical stretch by 2. Now we can do period. All right, taking a look back at my equation. Back at my equation, I take a look at that 3. That 3 isn't the period, but I do pi over that number, and that'll give me the period. So pi over 3. You can also take a look at the graph, and it's the distance from asymptote to asymptote. All right, then we've got phase shift. Well, taking a look in the equation itself, it looks like I went right pi over 3. And then my vertical shift, looking at the equation, it looks like I went up 1. Asymptotes, yes, I do have them. And actually, I'm going to do them before I even talk about domain. So my asymptote is going to be x equals, all right, let's just find one of them. And I normally go to the first one, so it's at 2 pi over 12. But I'm answering a question here, so I don't write 2 pi over 12, I'm going to write pi over 6. So it's going to be at pi over 6, plus or minus, though. Remember, this is just one period. We want to find all the asymptotes. So the beautiful thing about tangent is that you have actually 2 asymptotes on the graph. All you need to do is look and see how far apart they are. But if you recall what I said just a second ago, you can find the period by going from asymptote to asymptote. So the distance between the asymptotes had better be the period. So if we go for the asymptotes, pi over 6 plus or minus period. So that's going to be pi over 3. But I want all of them. So I use n. So I'm actually going to rewrite this. I want it to be pi over 3. But I want it to be all the pi over 3 distances. So I use n. And n represents an integer, 0, 1, 2, 3, 4, 5, so on and so forth. Once I know where my asymptotes are, I can do my domain no problem. I always do my asymptotes first, though, because my domain is going to be all real numbers except where the asymptotes are located. So x not equal to pi over 6 plus or minus pi n over 3. So the graph exists everywhere except at the asymptotes. The range, these are kind of the gimme points on the tangent graph. The range goes on forever. So because it doesn't have that max or min value, because it gets rid of any extrema, because it gets rid of any amplitude, we know that the range goes from negative infinity to positive infinity. All right. What else do we need? Probably even, odd, neither would be my guess. For even, odd, neither, I would do the exact same thing that I did. I'm going to go back to my graph, and I'm going to basically duplicate it. So, and I'm just going to basically take this section here, and I'm going to copy paste it to the left. So at the next increment I was up, then I was down at 1, then I went to -1, and then I had another asymptote. So I'm only duplicating this just so I can see my y-intercept and so I can see even, odd, neither. This is definitely going to be neither because it doesn't have symmetry to the origin. Remember, if it had symmetry to the origin, then it would be odd. So, but because this has that vertical shift, this doesn't have anything. So this is neither. But I can see my y-intercept right now. My y-intercept is going to be at 0, comma, looks like 1. That works out nicely. And then if we take a look at this graph, if we were to be asked to do increasing, decreasing, and constant, it's constant nowhere. But this graph is increasing over the entire domain, which means all real numbers except for the asymptotes. It's always going up. So if you're ever asked increasing and decreasing on this, and we'll talk about it more in class as well, based off of this graph, it's increasing the entire time except at the asymptotes. All right, I think that covers it for this question. Let's go on to the next slide. All right, so now we've got cotangent. Now we're going to get into the reciprocal functions. So what I'm going to do, and I'm going to pause for this entire thing, I am going to rewrite this as its reciprocal functions. Like, who belongs with cotangent? Well, it's tangent. So what I'm going to do is I am going to, I'll come back to this guy later. But for now, I am going to rewrite it as a tangent graph. And then I'm going to do the exact same thing. I'm going to do the entire thing that I did on the previous page. Go through, get all of my x and y points, perform the transformation, and get the graph. Then I'm going to stop. So I'm going to pause now. You might want to pause. Do this as if it were a tangent curve, and then we can pick up and talk about cotangent. Okay, so here's what I have for my tangent curve. So I went through and I performed the exact same transformation based off of the equation as if this were a tangent graph. So you'll see I set up my x's and my y's. I used my tangent points, not my cotangent points. Now, again, this is one way you can do it. You can go ahead and use the cotangent points if you want. But for me, I hate memorizing, and I can't stand it. So figure I already have the sine, cosine, tangent idea locked in my head. I don't feel the need to cram more in there. So I'm just going to go ahead and use what I already know. So I went through and did my total transformation on my x and my y points, and this is the tangent curve that I would come up with. Well, whenever I want to graph a reciprocal function for tangent, I normally like to have 2 periods of tangent in front of me. So what I'm going to do with this graph is I'm going to go ahead and just duplicate it. So I'm going to make another copy. You can either copy to the right or copy to the left. It doesn't matter. I just think that when I try to graph cotangent with only 1 period of tangent, I have a hard time seeing it. So I'm just going to go ahead and copy what I've got down here. So remember, I'm just going to basically copy paste this. So after an asymptote, it looks like I am down, then at -2, and then up, and then it looks like I have another asymptote. So again, I'm just creating 2 periods of my tangent graph. Just because I think it makes it just a little bit easier to see when I do cotangent. And then just to make sure that these are the exact same duplicates of each other, just to make sure that you went the same distance. So I see that I've got 1, 2, 3, 4 boxes in between my asymptotes. 1, 2, 3, 4 boxes in between my asymptotes. Just to make sure that I didn't throw it off a little bit. All right, now here comes the cotangent graph. You'll notice that I highlighted it in orange originally, so I'm just going to go ahead and go back to orange. So for my cotangent, let's go ahead and rewrite my equation in orange. Now, if you choose to do this on the test, you choose to use this method, you are welcome to color code it if you would like. I don't have a problem with that at all. Please make sure that it's perfectly clear which one is which, though, because these do look a lot alike. Okay, so I'm going to use the idea of what a reciprocal is. Well, reciprocal, back in your knowledge, it basically just means to flip something over. So that's what I'm going to do. I'm going to flip stuff over. When I do that, though, I have to do some ripping aspect as well. So in order to figure out where I'm supposed to rip, the first thing I need to do is go back to my graph. I'm going to grab another color, just so we can see it. Actually, I'll go back to black. And I want to find that equilibrium line. So where is that 0 line? Well, the 0 line looks like it's about right here. It's not an asymptote. I'm just trying to figure out where it's located, though. So I find that point, and it is any point that's actually located on that equilibrium line. I am going to rip my graph. So notice that this point here is actually located on the tangent curve and on that new 0, that equilibrium line. I am going to rip at that point. To rip means you create an asymptote. So I'm going to rip right there. And this is all in orange. This now represents my cotangent graph. Keep looking at my equilibrium line, and I see another point right there. That's also located on it. So I am going to rip at that point. Now, here comes the flipping. The beautiful part about this. With cotangent, you get to use the points that were already there. So, if I go back to the left here, notice this point that was on the tangent graph still is on the cotangent graph. So is this point, and this point. Those points still get used. Now, it looks a little crazy though. Okay, so we ripped, now we have to flip. Okay, so where there were asymptotes for tangent is now a 0 point for cotangent. So I find where all of my asymptotes hit that equilibrium line, and I give them an actual point there. Give them an actual point. An actual point. Now, what I'm going to do is I am going to see these 3 points right in the middle, between my 2 rips, my orange asymptotes. Let's go ahead and connect those. That is 1 period of cotangent, that orange right in the middle. Now, I can use the other points as well, the ones that I filled in, but they don't look complete to me, so I don't like filling them in. But if you feel the need to, just remember that it's a duplicate. So that would eventually continue down. And this one would be the down part, which would eventually continue up. So the orange is now our cotangent graph. So to create the cotangent graph, and this is how I do all the reciprocals, I graphed the tangent, and then I ripped at any point on that equilibrium, I created an asymptote, and then I used the points that were already there, the actual points that I plotted, but I flipped the graph itself. So notice that the black graph, the tangent, curves, the tails go up to the right, but on the cotangent, the tails go down to the right. So I have that flipping aspect of it. Now I go through and identify everything that I have. So based off of this, my vertical transformation, and I'm going to do this all in orange because this is all about the orange graph. The vertical transformation, well, the vertical transformation for cotangent is exact same thing for tangent. So it looks like I timesed by a half, which means this was a compress by 2. So I took all of them and divided them by 2. So they're not as stretched out anymore. Then I need to take a look at my period. Well, the period for cotangent is the exact same thing as the period for tangent. So it's going to be pi over b, which is going to be pi over 3. My phase shift is the same for cotangent as it is for tangent. So it looks like it was left pi over 3. My vertical shift is the same for cotangent as it is for tangent, is going to be down 2. All right, my asymptotes. Now, here's where I have to pay attention to the orange, because I am talking about the orange graph itself. It's going to be x equals, okay, take a look at the graph. It looks like one of the asymptotes is going to be at negative 4 pi over 12. So this one right here is at negative 4 pi over 12. Or you could even use this one here, which looks like it's at 0. Either one is fine. So I think I'm going to go with 0, because I don't have to simplify it, plus or minus the distance between the asymptotes for cotangent is the same as the distance between the asymptotes for tangent, which is the period. And the period in this case is pi over 3. So it's going to be pi n over 3. Now I can do my domain. My domain is going to be all real numbers excluding the asymptotes. My range is the exact same range as tangent, which is all real numbers. Then it looks like for increasing, decreasing, and constant, this isn't constant anywhere. And if you take a look at the orange curve, it's decreasing everywhere except for the asymptotes. So for decreasing, I would write the exact same thing as the domain. Everywhere, so all real numbers, excluding the asymptotes. So in this case, the decreasing is identical to the domain, whereas on the previous slide, the increasing was identical to the domain. Then, if we take a look at the y-intercept, well, it looks like we have an asymptote right on top of the y-axis, which means we don't have any y-intercept here. Doesn't exist, or none. And then, what else do we need? Oh, even, odd, neither. Even, odd, neither. Take a look at how this acts around the origin and whether or not it has symmetry to the origin. That's definitely not, because it's got that shift down of 2. And then we need to see whether or not it has that symmetry to the y-axis. Well, no. If I fold over the y-axis, they don't match up. So I think this one is also going to be neither. All right, so there's our graph of cotangent. Now again, you can go through, memorize the points for cotangent, or draw the little picture off to the side for cotangent and do it that way, just like you did with sine and cosine. Or you can just do tangent and rip it and flip it. So there's our cotangent. Let's take a look at the next slide. Okay, so now we're on to the other two reciprocal functions. So I'm going to do the exact same thing that I did previously with the cotangent. Excuse me, yes, with the cotangent on the previous screen. I'm going to go through and I am going to put this little cosecant off to the side. So when I come back to him, I'll be graphing the cosecant in blue. But for my purposes, I'm going to do the reciprocal for cosecant. Cosecant reciprocal is sine. So I'm going to go ahead and rewrite this as the sine graph. Another reason why it is super important that you know what the reciprocals are. Now that I have it rewritten as sine, I'm going to go ahead and do the exact same thing that I did previously. I am going to graph this as if it were sine. So right now would be a good time to pause, do the graph completely as sine, and then hit unpause and then see if we match. Then we'll go ahead and do the ripping and the flipping. Okay, so here is all of my work as if this were a sine graph. You'll notice that I ended up having to add pi over 8, and because I had to add pi over 8, I took my pi over 4s and my pi over 2s and my first table of my x's after dividing by 2 and made all the denominators 8 instead. And then I checked to make sure that the distance was the same again, so it looks like they're 2 pi over 8 apart from each other. Went ahead and graphed it. All right, so now let's actually create a cosecant graph. So I grabbed my blue pen. Let's go ahead and rewrite my blue equation here for my cosecant. So it's going to be y is equal to -2 cosecant. Took out a 2. X minus pi over 8 minus 1. All right. So I need to find that equilibrium line again. All right. So that 0 line. So for my sine, that's where those zeros are located. All right. Let's rip. So every point that is located from the sine curve on my equilibrium line is going to give me an asymptote. So this point here, that's going to give me an asymptote. This point also gives me an asymptote. And this last point here also gives me an asymptote. So anything that was a 0 point now becomes undefined when you flip it over, hence the asymptotes. All right, the points that were already there, so the actual peak and valley, those points get to be used. Now what we're going to do is we're going to flip. So if we take a look at this first section here on the black graph, so on the sine graph, it looks like it's a dip. So what I'm going to do is I'm going to flip it over, so now it becomes a bump. So what was a dip is a bump, and what was a bump is now a dip. Or I guess you could use the correct terminology and say what was a max is now a min, and what was a min is now a max. Okay, so now we have the blue graph is going to be our cosecant graph. So now from here, let's go ahead and identify everything that we need. So amplitude, none. Remember, if you're ever asked amplitude, it better be about sine and cosine. Everybody else has no amplitude. Period. The period for cosecant is the same as the period for sine, which is going to be 2 pi over b, which is going to be 2 pi over 2, which we would not leave as our answer. We would simplify it to pi. Phase shift for cosecant is the same as it is for sine. It looks like we went right, pi over 8. And then vertical shift for cosecant is the same as it is for sine, which was down 1. Now, I'm going to do my asymptotes. They're going to be x equals, take a look at the graph. It looks like my first one is at pi over 8. So I'm going to go ahead and use that, pi over 8, plus or minus. Okay, this is where I would highly recommend that you actually take a second and count. So these are all in pi over 8 increments. So from here to here is the distance between the two asymptotes. So if I'm at 1 pi over 8, then I go 2 pi over 8, 3 pi over 8, 4 pi over 8, 5 pi over 8. So from 1 pi over 8 to 5 pi over 8 is going to be 4 pi over 8, which is pi over 2. So this is going to be pi n over 2. We can also remember this because if you take a look at the graph, there are 3 asymptotes, one at the end, one in the middle, and one at the beginning, which means the asymptotes are half a period. If the period is pi, then the distance between the asymptotes is pi over 2, or half of the period. All right, now that we have the asymptotes, we can do the domain, which is going to be everything except where the asymptotes are located. The range. Well, we've got this big gap between them, so I always think of doing 2 different sections. So if I come from the bottom, it's going to be negative infinity. As I get close to this point, and that's going to be negative 3. And it hits there, but then it stops and it picks up again. It picks up again at this point here, which is going to be at 1. And then it takes off to infinity again. So for range, for cosecant and secant, we're going to have 2 different sections that we need to deal with. All right. I think one of the other things that we could do are probably the extrema. I'm not sure if it's asked in your notes. It might be, though. So let's do relative max. All right, remember we're looking at blue. So the highest blue point, so take a look at these in chunks, is going to be this point down here. That is higher than all of the other blue points in its immediate vicinity. So that is going to be at, let's see, there's 1, 2, 3 pi over 8. Plus or minus. Okay, notice that we're looking at the entire period of cosecant, and I don't see another maximum, which means I need another period to happen to get there. So I'm going to use the entire period to find the next one, comma, and then where's it at? Well, it's at a y value of negative 3. That's my relative max. Let's do my relative min. Same idea. Look for the lowest blue point in comparison to its surroundings, which is going to be this one over here. And that x value is at 7 pi over 8. We would have to see another period to see the next one, and its height is at 1. All right, even, odd, neither. Well, if we take a look at this, I'd probably have to repeat my graph back a little bit. So let's see, I've got 1, 2, 3, 4 spots in between my asymptotes. And then the next point would be up here to duplicate what I've got, and it would look like that. Notice that it hits the y-axis kind of in a funny spot, which means it's not going to be symmetric to the y-axis or to the origin. So this thing is definitely neither. And then at this point, to be able to find the y, the best I could do is show that I'm plugging in 0 for x. So I would do 0, comma, and I would go back. I get negative 2 cosecant, plug in 0, looks like I'm going to get negative pi over 4. And then minus 1. Well, this can be done. So, because pi over 4 is something that we're familiar with, so negative pi over 4. All right, here comes your knowledge of the unit circle. I know that this is going to be 0, negative 2 times. All right, so sine of negative pi over 4. When negative pi over 4 is down, which means the sine value is going to be negative. So sine is going to be negative root 2 over 2, which means cosecant is going to be negative root 2. So this is going to be negative root 2, and then minus 1. Multiply those together. It looks like it's going to be 2 root 2 minus 1, which I don't have a calculator, so I think I would just stop there. So there is a graph of our cosecant. On the next screen, we have a secant graph. This is based off of cosine. So go through, repeat the exact same process for cosine. I'm going to go ahead and pause, do all of my work for cosine, and then we can start ripping and flipping. Okay, so here's my cosine information. And when I went ahead and graphed this, I do the same thing for cosine that I do for tangent. I go ahead and graph 2 periods of it for you, just so you can see where the max and the mins are located and what happens with the graph. It's kind of hard to see just the way that cosine and tangent normally are to get their reciprocals. Okay, so here is the information that I got from my cosine. I'm going to go ahead and go back up to my original equation, and I'm going to do this in purple this time. So this is going to give me negative secant. Looks like I took a half out. I got x plus 6 pi. And then plus 1. All right. So now I'm going to do the exact same thing that I did previously. I'm going to find that equilibrium line, so 0 line for this graph. So that's where my equilibrium line is. And what I'm going to do is I am going to rip at any point on that line. So there's 1. So let's rip there. Here's another one. Rip there. There's another one. And another one. Then use the original points and flip. So it looks like it's going to curl up, which means now it's going to curl down. Use the original points. Looks like it's a bump. So now it's a dip. What was this one? It was a dip. Now it's a bump. And this one. So the purple is my secant graph. Now that I have it, I can go ahead and identify everything. All right, amplitude. Well, amplitude only exists for sine and cosine, so this is none, or D and E. Period. The period for secant is the same as the period for cosine, which, based off of this, looks like it's going to be 2 pi over b, which looks like it's going to be 4 pi this time, because it's going to be 2 pi over 1/2, which gives me 4 pi. My phase shift is the same for secant as it is for cosine, and it looks like it's going to be left 6 pi. My vertical shift, again, same for secant as it is for cosine, is going to be up 1. All right, now my asymptotes. It's going to be x equals, and just find one of them. It looks like the one that would have actually been there had I not continued on with 2 periods here would have been at negative 1, 2, 3. This one right here would have been at negative 3 pi. So negative 3 pi plus or minus, it's still going to be half the distance of the period. So half of the period times n, because we want all of them. And then that means that our domain is going to be all real numbers, excluding where all the asymptotes are located. My range, all right, I've got two pieces. So I know I'm going to come up from negative infinity to my lowest point, which means it's going to be this guy right here, which is at 0. That's kind of nice. And then it stops, then it picks up again to this point here. So it looks like it's at 2. And close it. All right, y-intercept. And this one is kind of nice. It's right on the graph. I can see it right here. It's right there. It's the beauty of extending my actual graph. So there's my y-intercept. This looks like it's at 0, 2. Even, odd, neither. Well, if you take a look at, I know it's hard to see because we've got black and purple kind of flying all over the place. But if we take a look at this, we've got the y-axis here. If you fold on top of the y-axis, the two different sides, so this right side here, is really going to match up with that left side there. So I think what we're looking at is probably an even function. All right, and then I know it doesn't ask, but let's go ahead and do the extrema anyway. So this point here on my far left, right there, that is going to mimic the same point at negative 2 pi. So this is going to be a max. So I'm going to have a relative max at negative 6 pi plus or minus. It looks like we have to go to negative 2 pi to get the next one, which is a 4 pi distance, 4 pi n, and it's at 0. So that's going to be a maximum for us, which means this guy up here, the next one over, that is going to be a min because it is lower than all of the other points around it. So we're going to have a relative min at, where's that at? So negative 6, negative 5, negative 4. Negative 4 pi. Have to go the entire length of the period, comma, and then it looks like it's up at 2. Okay. That's it for our reciprocal functions. So again, you can go through and memorize or find the points for the original and then just do it that way. Or if you want to do the ripping and the flipping, you really only have to memorize sine, cosine, and tangent.